resonance. Sorry, I just changed it and I missed because I just changed the topic. So just one sec. I think that we can do it online. So no issue. So basics of nuclear magnetic resonance spectroscopy. So that means it's a spectroscopic technique. So what is spectroscopy? We all know what spectroscopy is. So basically it's a branch of science which deals with the interaction of electromagnetic radiation with matter, right? And when we say electromagnetic radiation with matter, so what do we mean by that? We mean by that we take an electromagnetic radiation and we interact with the matter. And under certain conditions, there can be many phenomena like absorption, emission, scattering, or whatever. But under certain conditions, something happens between the electromagnetic radiation and matter. And we get an output, what we call as the spectrum. And from this spectrum, it is our smartness that what information we can extract out of that spectrum. And we, the chemists or the scientists, what we are interested in from the spectrum, we are interested in studying the structure of matter. So basically, we are trying to use it as a tool for structural elucidation. That is our basic purpose. That's the basic purpose for this studying spectroscopy in general or NMR spectroscopy in particular. So that means interaction of electromagnetic radiation with matter under certain conditions that are defined criteria. Under those conditions, we get an output, what we call as the spectrum. And from that spectrum, then we use our knowledge, our wisdom to extract the information about the structure. I said electromagnetic radiations. So what are electromagnetic radiations or what are electromagnetic waves? As you know that the electricity can be static. You know that if you take a balloon for some time and especially you are wearing some silky cloths, so you have a balloon in your hand for some time, after that you can just you can make it stick to the wall. So that is static electricity. Similarly, magnetism can also be static, like your refrigerator magnets, so which come in all shapes, heart shaped, star shaped, rectangular, circular, all shapes. So electricity can be static, magnetism can also be static. But when the electrical field and the magnetic field, they couple with each other, then we get the electromagnetic waves. So electromagnetic waves are formed when an electrical field, which here I have shown in yellow color, couples with a magnetic field that I have shown in mauve color. So when they couple together, we get electromagnetic waves. And in electromagnetic waves, the magnetic and the electrical fields of an electromagnetic wave, they are perpendicular to each other as well as perpendicular to the direction of propagation of the wave, So that is electromagnetic wave. And if we say electromagnetic wave, then we also come across another terminology, what we call as the electromagnetic spectrum. So what is an electromagnetic spectrum? So basically, spectrum means everything together. That is electromagnetic spectrum. So you see the arrangement of all types, the arrangement of all types of electromagnetic radiations in whatever order. You can take it as increasing wavelength, you can take it as decreasing wavelength, you can take it as increasing frequency, decreasing frequency, doesn't matter, energy, in terms of energy. So that means if you take two extremes, that means from one extreme to another, lower to the higher or higher to the lower, doesn't matter. The arrangement of all types of electromagnetic radiations in one order, in any one order, you see, that is what we call as the electromagnetic spectrum. And an electromagnetic spectrum, it covers all ranges, like you see, starting from the very, very low frequency radio waves to the very high gamma rays. And sometimes when we study it in books, then we think about that, oh, maybe I don't know what electromagnetic spectrum is. But in actual practice, you come across the electromagnetic spectrum on a daily basis. So there are hardly any ranges of electromagnetic waves which you are not already familiar with, even when you were in matriculation or when you were in your +2 or in undergrad or postgrad. So hardly there is any portion of the electromagnetic spectrum about which you are not, you have not interacted. Say, for example, you see visible light. That is also a part of the electromagnetic spectrum. So you always come across the visible light. Similarly, you tune into a radio station. So you are already coming in terms with the radio waves. So already you see the radio waves and the visible light. You see these two parts of the spectrum you are very much familiar, because none of us are here who have never used a radio. That means in your car or in your home. Similarly, you see, if you have a microwave in your home or ever used a microwave, so the microwave part of the electromagnetic spectrum, that is also used. Infrared, when you use a remote, so you see most of the remotes, they work on the infrared.
Sir, your mic is off.
I think.
Yeah, because the connection was lost. So let me again share it. Just 1 second. I think that we are back on the track. So you see X-rays. So you also come across X-rays when you go for some X-ray or for yourself or in your family. The only part part of the electromagnetic spectrum which might be new to you are the gamma rays, which means you're not directly associated with gamma rays. But that means you know a lot about electromagnetic spectrum. So when you just read it in a book, that electromagnetic spectrum, so there is no need to just think that, oh, how to cram it or how to learn it. So you already know a major part of the electromagnetic spectrum. But please remember, when we say electromagnetic spectrum, so that means arrangement of all kind of electromagnetic radiations in any order, increasing frequency, decreasing frequency, energy, wavelength, whatever. But we must remember that electromagnetic spectrum is continuous. So it is a continuous. Nature gave us a continuous electromagnetic spectrum, but we, for our own convenience, we just try to divide it into radio waves, visible, infrared, UV. So the dividing lines, because those have been provided by us, the people, the scientists, so dividing lines are arbitrary. And depending upon what kind of electromagnetic radiations are interacting with the matter, a molecule can undergo many kinds of excitations depending upon the energy, depending upon the electromagnetic radiation. For example, that if we have interaction of X-rays with matter, then the molecule can undergo electronic transitions. Similarly, in case of UV visible also, the molecule can undergo electronic transitions. But the difference is that in case of X-rays, the energy is high, of the order of about 300 kcal per mole. So in that case, we have, it can move electrons in atoms from the inner shells to the outer ones. So we call it as the electronic transition. Whereas in the case of UV visible, now the energy is low. So UV visible light, because the energy is 40 to 300 kcal per mole, that is less than the X-rays. So it can move only the valence shell electrons, and typically from a filled bonding molecular orbital to an unfilled anti-bonding molecular orbital. So both are electronic transitions, but in one case it is from inner to the outer shell, and whereas in the case of UV visible, then it is only and only the outer shell excitations. Then IR, you see we have vibrational excitations because the energy is still lower. Microwave energy is still lower, of the order of 10 to the power minus 4. So it can cause only rotation around the bonds. And radio waves, they have the least energy, of the order of 10 to the power minus 6 kcal per mole. So they are only capable of reorienting the nuclear spins. They're not able to do anything else. So then here we are dealing with the radio waves, the least energetic. And you see, living in democracy, many times we think that the might is right. That is more, if we have, means the more number of people, or more means the majority is authority. But in science, many times you would find that majority is not authority, because best example is from the, you see, the atmosphere, the trace gases, they hold the best chemistry in the atmosphere. So similarly here, radio waves, although they have the least energy associated with them, 10 to the power minus 6 kcal per mole, but still they provide us with the most powerful tool, one of the most powerful tool in spectroscopy, what we call as NMR, the nuclear magnetic resonance spectroscopy. So what is NMR? So basically NMR, nuclear magnetic resonance spectroscopy, it is nothing but it is a spectroscopic method, one of the spectroscopic methods. Spectroscopic methods for what? It is a spectroscopic method for structure determination. So it is one of the methods of structure determination. So what is the aim of studying NMR? The aim is very simple. First is to understand the basics of the NMR. That means the principle of the NMR, which is very important. And I know all of you know, but still you see, if you understand the basic, the principle of NMR, it becomes very easy to understand everything else. And by understanding the basic, understanding the principle of NMR, the basic aim is to reach a stage where we can interpret some simple NMR spectra, or we can say where we can identify simple structures from the NMR spectra. So when I say that it is a method of structure determination, then you see this, all spectroscopic techniques, they were developed only, you see, after the second half of the 20th century. But great chemistry has been done prior to that. You see the Sheehan synthesis, the cholesterol synthesis, Woodward synthesis, great chemistry has been done. So the question comes, obvious question comes to our mind, that how we used to determine the structures when we didn't have spectroscopic methods. Of course, we used to determine structures, and the methods that we used to use at that time for determining the structure of the compounds, that is called the classical methods. We also call them as chemical methods or degradative methods. Why? Because in these classical methods, what we used to do, that will be determining its structure based on the identification of various functional groups by the chemical tests, and along with the results of the degradation studies, that under basic conditions, what it gives us, under acidic conditions, what it gives us. For example, let us say that we have an unknown compound and that you get in your lab, in your organic chemistry lab, and you want to find out whether there is an unsaturation, a double bond present or not. So what you do, either you can do a catalytic hydrogenation, or in your lab, you can do a simple experiment adding bromine CCl4. So if bromine adds up, so you would say that there is a unsaturation, there is the presence of a double bond. If we want to know the location of the double bond, then we'll do the ozonolysis. After the ozonolysis, we'll identify both the components, and with the identification of the two components, we'll come to know that, okay, whether the double bond is between C3 and C4, or C4 and C5, or C7 and C8, right? Likewise, so what we used to do, we'll do the degradation studies. We'll try to have this functional group studies based on these chemical tests or degradative methods. And once we have all those tests, on the basis of that, we'll propose the candidate structure, the most probable structure. And then we'll do a complete synthesis of that probable structure. And if the synthesized compound matches with the compound that we isolated, which was unknown, if it matches in all characteristics, all properties, then we'll say that we have the structure of the compound as right. If not, then sometimes you see that the chemists, the great chemists of the last century, they struggled for sometimes 40, 50, 60 years for the structure of compounds. But all these, you see, all the classical methods, chemical methods, degradative methods, they have been pushed in the back by the development of, by the advent of the modern methods, what we call as the instrumental methods or the spectroscopic methods. And slowly, these methods, they have given way to all those, you see, degradative methods. And there are so many, you see, there's so many spectroscopic methods or instrumental methods available. But the most important being the NMR, the nuclear magnetic resonance spectroscopy, which gives us about the carbon, which tells us about the carbon skeleton that is the carbon skeleton as well as the environment of the hydrogens which are attached to it. IR, which reveals the presence or absence of key functional groups, like the presence of carbonyl or the absence of carbonyl, presence of nitrile or absence of nitrile. Similarly, UV visible spectroscopy, it probes the electron distribution, especially in the molecules that have conjugated or pi-electron systems, and mass spectrometry, which gives us the molecular weight and formula, both of the molecule as well as of the various structural units within it. Now you see, although these structural, you see, although these techniques, they are quite diverse. They look like quite diverse. NMR, IR, UV visible, mass, they look quite diverse. But basically, you see, they converge. They do not compete with each other. They are complementary to each other. They do not compete, they are complementary. So you cannot say NMR is better than IR or IR is better than UV visible or mass is better than NMR, because there is no competition between these techniques. They only complement each other. I can give you an example. Say, for example, that presence or absence of a functional group, let us say of nitrile, that you can do so easily on the basis of a 10 lakh rupees machine, IR machine, which you may not be able to do it that easily on a 4 crore NMR machine. Right? So they do not compete with each other. They complement each other. So we use all our knowledge, all our information based on these spectroscopic techniques to arrive at the structure of a new molecule. So they are complementary. Please remember in mind. On one hand, I say that they are complementary. There is nothing better than like a competition. At the same time, I would say that out of all these techniques, definitely NMR is the most powerful tool. The most powerful tool, because we get the maximum amount of information from NMR. So they complement each other. Every spectroscopic technique has its own significance, but they are not competing. And NMR is, if you want to agree that it is the most powerful, then I would say one of the most powerful tool in the hands of chemists. Now, historically, you see, Rabi was the first physicist. He was the first who predicted and observed the phenomena, the basic phenomena of NMR. But the first observation of the NMR signal in the bulk that was made independently by Edward Purcell at the Harvard University and Felix Bloch at the Stanford University simultaneously in 1946. They didn't know each other. They were not talking to each other. But surprisingly, they had this idea at the same time. And in 1951, to apply that to find out the structure of ethyl alcohol. Now, please remember, in 1951, we were knowing the structure of ethyl alcohol from many centuries. So ethyl alcohol was not new, but the technique that was applied to confirm that, yes, this is the structure of ethyl alcohol, that was new. Once this happened, after that, this field never looked back. Then in 1953, NOE was applied. 1966, Ernst and Anderson, they applied the concept of Fourier transform, FT, which is a Fourier transform theorem, which is a mathematical theorem. They applied it, and please remember that if this FT would not have been applied in NMR, then carbon-13 would not have been possible. 1975, Zener and Ernst, they developed the 2D NMR techniques. 85, Wuthrich used it for the first solution structure of a small protein. 87, 3D NMR, 90, pulse field gradients, 1996, new law structural parameters. So this field kept on developing at a very, very fast pace. Now look at the outcome for general public. You see, Rabi got the first Nobel Prize in physics in 1944. And Purcell and Bloch, they got the Nobel Prize in Physics in 1952. Now here it is very, very important. You see, 46, the first NMR of bulk, 51, the first application to prove the structure of ethyl alcohol, which we already know, which we knew at that time. But within 1 year of the first application and within 6 years of the first NMR of bulk, Purcell and Bloch, they were given the Nobel Prize. Normally, it takes on an average 15 to 20 years from the time when the seminal work to the time when the Nobel Prize is awarded. But here you see the scientific community knew that we have something so revolutionary at hand that within 1 year of its first application, a Nobel Prize in Physics was given. In 1991, Ernst got the Nobel Prize in Chemistry for the application of FT. In 2002, Wothrich got again in chemistry for 3D NMR. 2003, Lutterbeer and Mansfield, they got the Nobel Prize in medicine. So here, one more thing is very important. You see, this is something, NMR is something which was initiated by the physicists and then hijacked by chemists for structural determination and then adopted by biologists for the benefit of humanity. Something started by physicists, then exploited to its hilt by the chemists, and then adopted by the biologists, because when you go MRI, what is MRI? MRI is nothing but basically NMR of your brain, of your body, where whatsoever part we are going for MRI. So that tells us that sometimes when we talk about super specializations, the cubicalization of the science, that is not important. So science is just one, as the planet Earth is one, and then we divided it into, say, India, Pakistan, Afghanistan, Australia, USA. Likewise, nature gave us only one science. So we compartmentalized it like it is physics, it's chemistry, it's microbiology. So it's for our convenience, but otherwise all sciences converge. But now you see, it is almost just 70 years for first observation of NMR. And this NMR has established itself as one of the most important spectroscopic tools for chemists in general and for organic chemists in particular. Nowadays, it doesn't matter which branch of chemistry you deals with, you cannot survive without NMR. So NMR, the name says nuclear magnetic resonance. That means it's a phenomenon which occurs in the nucleus, which occurs when the nuclei of certain atoms, they are immersed in a static magnetic field. That means magnetic means it involves magnets. That means certain nuclei, when they are immersed in a magnetic field, then some of those nuclei, they undergo a phenomena in the nucleus, what we call as resonance. So that is why we call it as the nuclear magnetic resonance. And we denote it as 1H NMR, that is the proper name, but we also sometimes call it as PMR. But the most appropriate name is 1H NMR. And what information we get from a 1H NMR spectrum of a compound? We come to know the number of different types of hydrogens present in a molecule. Then we come to know the relative numbers of different types of hydrogens, the electronic environment of different types of hydrogens. That means whether those are attached to electronegative atoms or electropositive atoms, and the number of hydrogen neighbor a hydrogen has. NMR spectrum. So now with this brief introduction, we come to what's the principle of NMR. Now we all know, you all have studied, we all know that the principle of NMR is spin. But what is spin? So basically, you see all nuclei, they have a property called spin. And spin is a fundamental property of the particle, just like electrical charge or mass. That's a fundamental property. As charge and mass are fundamental properties, spin is also a fundamental property. It comes in multiple of half, and it can be positive or negative. That means spin can be plus half, minus half, plus 1, minus 1, plus 1.5, minus 1.5, multiples of half. And protons, electrons, and neutrons each possess spin. So it is not electronic spin you are very much familiar with, but you do not talk most often about the spins of neutron and protons. But protons, electrons, and neutrons each possess spin. And the last part, please remember this. This is very important for understanding NMR. The last characteristic of spin is that individual unpaired electrons, protons, and neutrons each possess a spin of half. This is very important. You note it. I'll use it many times in my lecture. So individual unpaired, I'm not talking about paired. Paired, the spin would be cancelled. Individual unpaired electrons, protons, and neutrons, they each possess a spin of half. For example, let's take the case of deuterium. Deuterium H, 2H. Now deuterium has everything single. It has one electron, one neutron, and one proton, as they have been shown here by the color code. So one each. So one electron has to be unpaired, one neutron has to be unpaired, one proton has to be unpaired. So because one electron is unpaired, so total electronic spin, we said each each unpaired electron, proton, and neutron possess a spin of half. So one unpaired electron, so total electronic spin for deuterium is half. Total nuclear spin, half due to one unpaired neutron, half due to unpaired proton. So half plus half, 1. So deuterium would have total electronic spin as half and total nuclear spin I is equal to 1. Right? Now take the case of helium, which has everything double. Now, in case of helium, you see everything is double. It has 2 electrons, it has 2 protons, and it has 2 neutrons. So now 2 electrons paired, so that means no unpaired electron. 2 protons paired, no unpaired proton. 2 neutrons paired, no unpaired neutron. So that means total electronic spin 0 because no unpaired electron. Total nuclear spin I 0 because no unpaired proton, no unpaired neutron. So that means now we can understand that the principle is nuclear spin, and NMR phenomena, it can be displayed only by those atomic nuclei which have non-zero spins, whose spin I is greater than 0. It should not be 0. If it is 0, there is no spin. So that means that would be NMR inactive. Now, what are the rules to find out nuclear spin? Now, most of the books, they provide you with 2 tables to find out that what are the rules to find out nuclear spin. One table, which is given in many books, which says that if the number of neutrons and the number of protons are both even, that is neutrons even, protons even, then the nucleus has no spin, I is equal to 0. For example, you see carbon 12, oxygen 16, so I is equal to 0. So neutrons and the number of protons both are even. Second is when the number of neutrons plus, that means you add number of neutrons plus the number of protons is odd, then the nucleus would have a half integer spin. That means I is equal to 1 by 2, 3 by 2, 5 by 2. So half integer. And if the number of neutrons and the number of protons are both odd, then the nucleus would have an integral spin. That means the spin would be 1, 2, 3, etc. That is one table which is given in many books. But most of the other books, they have given this table, which says even atomic mass and even atomic number, no spin. For example, carbon 12, oxygen 16. Or even atomic mass and odd atomic number, whole integer spin. That is I is equal to 1, 2, 3. Right? And if we have odd atomic mass, then the spin would be half integer. That is 1 by 2, 3 by 2, 5 by 2. So these tables are good for cramming, just for understanding that when the nuclear spin would be 0, when the nuclear spin would be half integer, and when the nuclear spin would be full integer. So that is good to find out whether a nuclei is NMR active or inactive. But it cannot explain that when a nuclei would have spin of 1 by 2 and when it would have 3 by 2 and it would have 5 by 2. It cannot explain when the nuclear spin would be 1 or 2 or 3. So none of these tables tell us that. It only tells us 0, half integer, full integer. So that means how we can come to know that sodium 23 has a spin of 3 by 2. We can come to know by going back to the fundamental property of the spin, the number 4 that I asked you to remember, that each unpaired neutron, proton, and electron would have a spin of half. So that means we can calculate the number of unpaired protons, we can calculate the number of unpaired neutrons, multiply each by 1 by 2, that would be the nuclear spin. So with that way, you can say for sodium 23, we have one unpaired proton and 2 unpaired neutrons. So 1 unpaired proton, so the contribution of proton towards nuclear spin is 1 into 1 by 2, half. Contribution of 2 unpaired protons, 2 into 1 by 2, 1. So total nuclear spin is 1 plus half, that is 1.5, that means 3 by 2. So that is the sure short way, that is the actual way to find out that what is the nuclear spin. So that means now we come to know that how to find out the nuclear spin I. And for each nucleus with spin, the number of allowed spin states it may adopt is determined by its nuclear spin quantum number. So for each nucleus, the spin quantum number or the allowed spin states or orientations, it is given by the spin. That means it is given by 2i plus 1, where I is we have just found out that the spin. So depending upon I, any nuclei would have allowed spin states or allowed orientations, and that would be given by 2i plus 1. So, and these spin states, they are quantified. That means they will go from minus I to plus I or plus I to minus I. For example, if we take the case of proton, for hydrogen, 1h. For 1h, I is equal to half. When I is equal to half, that means allowed orientations for 1h are 2i plus 1. That means 2 into 1 by 2 plus 1. So 1 plus 1, 2. So this tells us, these are quantized. So it tells us that why a hydrogen, 1h, can adopt only 2 orientations. When we say E1, E2 or alpha, beta, so hydrogen can adopt only 2 orientations. Those are half and minus half. That means only 2 energy states, 2 energy levels are possible for 1h, for hydrogen, for a proton. Only 2 energy states, energy levels are possible. Another important parameter here is of every particular nuclei is the magnetic moment. And magnetic moment, we can express it as mu is equal to gamma I h by 2 pi, where you see mu is the magnetic moment, h is the Planck's constant, and gamma is the magnetogyric ratio or the gyromagnetic ratio. And here you see, I would like to say here something, that when we study NMR as a tool for structural elucidation, there is no need, there is absolutely no need of heavy mathematics. In fact, we should not involve the heavy mathematics here. The mathematics behind NMR is required only if you go for a research in the field of NMR, where you are trying to develop the new gradients, where you are trying to develop the new methods to acquire NMR for the instrumental technique. But if you are using it as a tool, then there is no need of heavy mathematics. I can compare it to a doctor. When you go to a doctor and you say, oh, I have some, I think that I suspect that there is something wrong with my heart. So he says, first of all, you go for an ECG. So he sends you to a radiographer. You go there, takes the ECG. You take that ECG, that piece of paper, that's also a spectrum, to the doctor. Doctor immediately sees it and tell you, oh, your heart is fine, or there is one tone is missing, or something. But suppose that there goes something wrong with the ECG machine. Does the doctor know that what is wrong with the NMR, with the ECG machine? No, because doctor only knows how to read that ECG. He or she is using ECG as a tool to identify the condition of the heart. In the same way, when we are using NMR as a tool, we do not need the spectrum. We need to use it as a tool to study the NMR spectrum, to interpret the NMR spectrum. So NMR spectrum, in the case of chemists, in the case of NMR, is equivalent to the ECG in the case of that for the condition of heart. So there is no need of heavy mathematics. So I said that mu is equal to gamma I by 2 pi, where gamma is the magnetogyric ratio, and the magnetic gyric ratio, it depends upon the nature of each nuclei. Each nuclei. That means a particular nuclei would have a particular value of the magnetogyric ratio. For example, for 1H, it is 267.513, whereas for carbon 13, it is almost 67.262. At the same time, if you look for fluorine 19, is 251.662. And magnetogyric ratio is important for our understanding of NMR, because higher the magnetogyric ratio, more is the magnetic field associated with it. So more magnetism associated with it, right? We can say that strength of the magnetic fields is described by the magnetogyric ratio. So higher the magnetogyric ratio, higher the magnetic field associated with it. So now we know that the principle of the NMR is nuclear spin, right? And as the nuclei has charges, we know that the nuclei has charge. So we can say a spinning nucleus is behaving like a spinning charge, right? We have a nucleus is spinning, and nucleus also has charge. So we can say a spinning nucleus is behaving like a spinning charge. And as all spinning charges, they produce a magnetic field. All spinning charges, they produce a magnetic field. So we can safely say that my spinning nuclei behaves like a tiny magnet. And if it is behaving like a tiny magnet, that means the magnetic field is associated with it. That means it would have a magnetic moment. So every spinning nucleus would have a magnetic moment, and different nuclei would have different magnetic moments. Now, for understanding our NMR, we need to look at the magnets. But here I would like to say another word of caution for the teachers as well as for the students. Whenever you want to understand NMR, never think about the bar magnets. Most of the books describe NMR by using these bar magnets, but bar magnets creates the biggest confusion in the mind of the students. So whenever you are dealing with NMR, never ever use these bar magnets. Always imagine the magnet as a spherical magnet. And you see, in the age of these students, it is very easy to imagine spherical magnets. When we were young, we always saw only the bar magnet. Our only interaction with a circular magnet, not even the spherical. A circular magnet, if we have to look at a spherical magnet, then we have to break the radio of our, the father, because only the speakers used to have the round magnets, not even the spherical ones. But nowadays, you see, you are used to seeing all kinds of magnets, even the refrigerator magnets you see of all sizes, all shapes. So for understanding NMR, you must in your mind, whenever you imagine a magnet, it should be a spherical magnet and not a bar magnet. So now we say that the principle is nuclear spin, and spinning nucleus is behaving like a spinning charge and would have a magnetic moment. So now let's consider a proton, because to understand that how these particles will spin, they behave in a magnetic field, nuclear magnetic resonance. How a nucleus behaves in an externally applied magnetic field. So to understand that how a particle or how a nucleus will spin, behave in a magnetic field, let's consider a proton. And this proton has a property called spin. That means it is a spinning proton, right? And because it is a spinning proton, proton is positively charged, so there would be a magnetic field associated with it. So it would have a magnetic moment. So as I said, let's not talk about this bar magnet with the north and south. We can talk about a spherical magnet that can also have north and south. And I have shown it with a color code. So red means north and the green means south, right? So now that this spherical magnet, a proton is spinning, that means a magnet with the north and south, it is spinning. Now the question arises, nuclear magnetic resonance. How a nucleus, this is my nucleus now. My nucleus is a tiny magnet. It's a spinning charge, it's a spinning magnet having a north and south pole. So now we need to understand NMR, nuclear magnetic resonance. That means what happens to this nucleus? Nucleus means spinning charge, spinning magnet. What happens to the spinning magnet when we immerse it in an external magnetic field? So that is the question in the story then. Okay, what would happen to it? What would happen to a proton? What would happen to a hydrogen when we immerse it in an external magnetic field? Miss Poonam is having something important. So if the
Dear
host
participants, yeah, please switch off your mics. Please mute yourself. Priyal, mute everybody except the speaker.
Yeah, I think the co-host can do it. So, okay, so in the ground state, all the nuclear spins, they are disordered. There is no order in it. They are disordered, right? And there is no. So this is a condition what we call as degenerate. Degenerate, they are degeneracy. Now, actually, you see the nuclei behave like this as the animation at the bottom. But for our understanding, we can show it that there is no order. You see, disorder, all directions. My spins are in all directions. So they are degenerate. There is no energy difference, right? But what would happen when I immerse it in an external magnetic field? Now, when a molecule containing hydrogen is placed in a strong magnetic field B0, this is the B0. For our understanding of the NMR, we would always assume that our applied magnetic field is from the bottom to top. So just by convention, we'll always assume, because that will make the things easy. So now when a molecule containing hydrogen is placed in a strong magnetic field B0, the magnetic hydrogen nucleus, it can attain only two orientations, because we said M is equal to 2I plus 1. So for H1, I is equal to half. So it can have only two orientations. And what would be those two orientations? One would be aligned with the magnetic field, applied magnetic field, and the other would be against it, opposing the applied magnetic field. So it would be having only two orientations. And that we can see like this, as most of the books show by the bar magnets. In the bar magnets, you can see here south north, south north. So that is aligned. North north, south south. That is against. That is not aligned. But I say, as I again say, that we should not look at the bar magnets for our understanding of NMR. We should look at the spherical magnets. So we can see here by the north south or by the color code. So here you see green red aligned, green green, red opposed. That means now we reach the two energy levels. The moment we reach two energy levels, definitely one of these would be high energy. So which one would be high energy? Definitely that state in which nuclear spins are aligned with the field, that would be low energy. Now this is the applied magnetic field, north and south. So here it is aligned, north south, north south. So that spin state, that energy state, that energy level where the nuclei are aligned with the applied magnetic field, that would be of low energy. And the other one where the nuclear spin are aligned against the applied magnetic field, those would be of high energy. And whenever we have two energy states, two energy levels, what we do in science, we always try to have a transition between the two energy states. So now we reach this stage where we understand that there are two energy states. One is high energy, one is low energy. So if we have two energy states, E1 and E2, high energy and low energy, so we can have a transition from the low energy state to the high energy state. How we can have it? We can have it by giving a photon. So a particle in the low energy state, it can absorb a photon and it can end up in the higher energy state. But the important thing here is that the energy of this photon must exactly match the energy difference between the two spin states. That is the important criteria here. It must exactly match. What to say? Say, for example, that NMR is a bus, right? And to go from to right, or say Ujjain to Indore, and the fare is for the bus is 165 rupees. So you have so many possibilities. You can give 200 rupees, conductor would give you 35 back and the ticket. You give 500, you will get money back. You can give 100 plus 50 plus 10 plus 5. You can give 10 into 16 and 1 into 5. So many permutation combinations you can give. You can give a 2000 rupee note and still you would get the ticket and you would get your money back. But if it is an NMR bus, then you can board the NMR bus only if you have a single note of 165 rupees. You cannot board it with a 200 rupee note. You cannot board it with a 2000. You cannot board it with 100 plus 50 plus 15. That is what I mean to say, quantized. The energy of the photon must exactly match the energy difference between the two states. And what is the difference between these two states? The difference is only that in the low energy state, we have north, south, north, south. In the high energy state, we have north, north and south, south. Excuse me. So now if I give a photon whose energy is exactly the same as the energy difference between E1 and E2, energy would be absorbed and the phenomena of resonance, what we say, that would take place. Say for example, here I give a photon, I give energy. So now you see what happens when I give energy, it goes from the low energy state to the high energy state, from E1 to the E2. How much energy? By absorbing energy, delta E is equal to H nu, right? And this energy difference between E1 and E2, it can be represented by an energy level diagram. Say for example, here in this diagram, on the x-axis is the magnetic field, on the y-axis is the energy. And you see when there is the magnetic field, let us say that this is zero. So when there is no applied magnetic field, then there is no energy difference. So all nuclei are degenerate, they are randomly ordered, they are disordered. So they have the same energy. But now you see, if I try to apply external magnetic field, more the applied magnetic field, more is the separation between E1 and E2. Clear? At zero magnetic field, no energy difference. But more the applied magnetic field, more the separation. So I can say that the energy difference between the low energy state and the high energy state is directly proportional to the strength of the applied magnetic field. That is why when we'll study the concept of chemical shift, so you will say that it will depend upon the chemical shift would depend upon the applied magnetic field or the operating frequency of the machine. So energy difference between the two spin states is directly proportional to the strength of the applied magnetic field. So if this is the applied magnetic field, then the energy then the two states would have energy E1 and E2, and the difference between E1 and E2 is given by delta is equal to H nu. So if we have a photon equal to the energy this delta E, exactly matching the energy delta E, there would be transition from E1 to E2. But here it is very important to understand that what is happening when we apply the external magnetic field. Suppose that we put 2 million nuclei in an external magnetic field, 2 million nuclei of ethanol, let us say. Now, when we apply an external magnetic, when there is no external magnetic field, 0 Tesla magnetic field, then all 2 million would be degenerate, would have the same energy. But now when I go to 2.35 Tesla, that means about 100 megahertz, now what would happen? Out of this 2 million, only 16 nuclei would be more in the lower energy state as compared to the higher energy. You see, this I have taken from Pavia, but this is wrong. I didn't get the time to change it. It has to be 1 million plus 8 and 1 million minus 8. So it is oversimplification where they are showing, they are only trying to show that there would be 16 nuclei more in the lower energy state. If you see, we had 2 million, here we have 1 million and 1 million plus 16. So we cannot convert 2 million into 2 million plus 16. So it has to be 1 million plus 8 and 1 million minus 8. So that is given by the Boltzmann, the Maxwell-Boltzmann distribution, which is n upper by n lower is equal to e to the power minus delta E by kT or e to the power minus h nu by kT. So out of 2 million nuclei at 2.35 Tesla or at 100 megahertz, there are only 16 nuclei more in the lower energy state. That means out of 2 million, the NMR phenomena is being given by only 16 nuclei. 2 million minus 16, they cancel out each other. They're simply cancelling out each other. If we go to 9.4 Tesla, then we have 64 nuclei in the lower energy state. If we go to 18.8 Tesla, then we have 128 nuclei. So at 100 megahertz or 2.35 Tesla, 16 nuclei. At 400 megahertz or 9.4 Tesla, we have 64 nuclei. And at 800 megahertz or 18.8 Tesla, we have 128 nuclei. So there's a very, very small excess number of nuclei in the lower energy state. And it is only this small population difference that is giving us the phenomena of NMR. So that is why sensitivity in case of NMR is a very big issue. That is why we have very expensive machines for NMR. And this such a small population difference, it presents a significant sensitivity problem for NMR. Why? Because you see, all other nuclei are cancelled to each other. They are not giving NMR. They cancel each other. So now we are ready to understand the mechanism of absorption. What did we say? We said we take a nuclei, we put it in an external magnetic field. When we put it in an external magnetic field, then it would be able to adopt only two orientations, aligned with the field, opposed to the field. Now we have two spin states, two energy states. Now, if we measure the energy difference between these two and give a photon exactly equal to the energy difference between E1 and E2, so well, the energy would be absorbed, right? And we'll say that the resonance has taken place. In fact, what we are doing in NMR, rather what we do in all spectroscopic techniques, we do not do anything more than measuring the energy difference between E1 and E2. That is what we do. So now let's imagine a nucleus of spin half in a magnetic field. And this nucleus is in the lower energy level. That means it is spinning on its axis. Now, in the presence of an external magnetic field, it will not lose its property of spinning, but it would also start precessing around the magnetic field. In the absence of magnetic field, disordered, no order. The spin is still there. But when we apply external magnetic field, the spin would be there, but along with spin, there would be a precessional motion also. That you see in this gyroscope. You see, it has two types of motion. One is spinning on the axis, and the second is the precession around the direction of the applied magnetic field. And the frequency of the precession, not the spin. Spin is the basic property, but precession has been generated by the application of the external magnetic field. So now the frequency of the precession, we call it as the Larmor frequency, right? Or the transition frequency. And the Larmor frequency is directly proportional to the applied magnetic field. More the applied magnetic field, more is the Larmor frequency. Why? Because more the applied magnetic field, more is the energy difference between E1 and E2, more is the population difference. And stronger the applied magnetic field, higher the rate of precession, right? Now, because this nucleus has a charge, so the precession also generates an oscillating electrical field of the same frequency. So we are applying electrical field, they are precessing, that means the charge is precessing. So what we said, electromagnetic, if a charge is precessing, it would have an electrical component associated with it. So this precession would generate an oscillating electrical field of the same frequency. And now what we did, we took the nuclei, applied an external magnetic field. Due to this externally applied magnetic field, we had a precessional frequency. Now, when we have this precessional frequency, now if I apply a second radio frequency, if I apply an external radio frequency wave, whose frequency is tuned exactly to the same frequency, that is my Larmor frequency. You're understanding? I took a nuclei, put it in an external magnetic field, it aligned itself in E1 and E2, and it had a precessional frequency. It started precessing, what I call as the precessional frequency. Now, if I apply a radio frequency wave, which matches the frequency of the precessional frequency, then what would happen? The moment they match, there would be a transfer of energy. So energy can be transferred from the incoming radiation to the nucleus. And what it would do, it would make it jump from E1 to E2. What is the difference between E1 and E2? The difference is only in the E1, if north is up, south is down, then in E2, north is down, south is up. And this is exactly what you can see here. When I give delta is equal to h nu, when I give the radio frequency, which is exactly equal to the Larmor frequency, what would happen? It will flip. So from the aligned state, it will come to the opposed state. And this is the condition, what we call as the resonance. And we say that the nucleus is having the resonance, nucleus is in resonance with the incoming electromagnetic wave, right? So we say delta is equal to h nu. We also say delta is equal to gamma h b0 by 2 pi. So from these two equations, once again, not involving heavy mathematics, we can say nu is equal to gamma b0 by 2 pi. So this is the basic NMR equation. Nu is equal to gamma b0 by 2 pi. This is the basic NMR equation where delta is the energy difference, h is the Planck's constant, b0 is the strength of the externally applied magnetic field, gamma is the magnetogyric ratio, which is constant for all protons. And because it depends on nuclei, carbon-13 would have a different magnetogyric ratio as compared to 1H. And nu is the frequency of the electromagnetic radiation. So we say this is the basic NMR equation. Now, for example, for a proton of a magnetic field of 23,486 Gauss, then the frequency needed to cause a flip from plus half to minus half would be based on nu is equal to gamma b0 by 2 pi. So when you do the calculation, we get 100 into 10 to the power 6 per second, that is 100 megahertz. Now, if we look at this basic NMR equation, nu is equal to gamma b0 by 2 pi, then all the protons in a compound should give a single peak due to the interaction of the radio frequency energy and a strong magnetic field. Why? Because you look here, nu is equal to gamma b0 by 2 pi. Gamma is magnetogyric ratio. We are recording 1H NMR spectrum. So gamma is same for all protons. All hydrogens would have the same gamma, right? 267.53 or 26,753 per second per Gauss. So gamma is same for all hydrogens. B0 applied magnetic field is the same. Pi is constant. So there is no variable. Everything is constant for a particular nuclei. For carbon-13, gamma is 1. For 1H, gamma is 1. So if this basic NMR equation is right, then all protons in a compound should give a single peak. But we know that we do not get a single peak. If we would have got the single peak, then NMR would have been of no use to us. We know that we get different signals. So then the next question comes in the story. Why we are getting different signals if this is my basic NMR equation? That means we defined somewhere, we did not take into account something. We are overlooking something. What we are overlooking? We are overlooking that we are saying that because gamma is same, B0 is same, 2 pi is same, so precessional frequency should be same, Larmor frequency should be same. But fortunately, the precessional frequency is not the same, even if we apply the same applied magnetic field. Why it is not same? Because what we have done, we are only talking about nucleus as if the nucleus is in isolation. But you know the nucleus is not in isolation. No nucleus is a bare nucleus. कोई nucleus अकेला नहीं रहता. No nucleus is a bare nucleus. And every nucleus is surrounded by electrons. And electrons are also charged. And we did not take into account the impact of electrons on our Larmor frequency. So when we apply an external magnetic field, not only my nucleus is spinning, but my electrons are also spinning, right? So electrons also circulate about the direction of the applied magnetic field. And based on that, you see this circulation of electrons around the nucleus, it causes a small magnetic field at the nucleus, which opposes the externally magnetic field in the middle. And we call it as the induced magnetic field. This is very important. We were considering only as if we are putting an isolated nucleus in an external magnetic field. But nucleus is not isolated. No nucleus is a bare nucleus. It has associated electrons with it. So due to this external magnetic field, electrons also circulate around the nucleus, and circulation of electrons, because they are also charged, so that also generates in magnetic field what we call as the induced magnetic field. And this induced magnetic field always opposes the externally magnetic field in the middle. Here I would like to say one thing. The circulation of electrons is as shown on your right. That is the true representation, true animation. But the picture that I have drawn in this, you see the animation that I have drawn in the PowerPoint, this is very important for our understanding. Although the actual representation is on your right. So what we say that here is the nucleus. When I apply external magnetic field, then the electrons start to circulate in such a way that they generate an induced magnetic field which is opposing B prime. This is my induced magnetic field, which is opposing the applied magnetic field in the center, in the middle. In the middle is very, very important, right? So what would be the impact of this induced magnetic field? That means now, although my applied magnetic field is B0, but what would be the effective magnetic field felt by my nucleus? The effective magnetic field felt by my nucleus would be a combination of the externally applied magnetic field B0 and the induced magnetic field. I'm deliberately using the word combination. Although you know that what it is, it would be B0 minus B prime. But you would see that why I'm deliberately using, because it is B0 plus minus B prime. So it is still a combination. So the effective magnetic field felt by the nucleus would not be B0, although I applied the magnetic field as B0. So that would be a combination of the externally applied magnetic field and the induced magnetic field generated by the circulating electrons by the electron cloud, right? So what does that mean? That simply means that the electrons around the nucleus, they are shielding the nucleus from the full force of the externally applied magnetic field. And in the story, we have now come to the concept of shielding and de-shielding. So that means the impact of electrons, which we did not take into account when we said the basic NMR equation is nu is equal to gamma B0 by 2 pi. Now we have come to a stage where we say B0 is the same, but the effective magnetic field felt by the nucleus would not be B0. That would be a combination of the B0 and the induced magnetic field B prime. So that means the electrons around the nucleus, they are shielding the nucleus from the full force of the applied magnetic field. So we say that that is a concept of shielding and de-shielding. Say for example, here I have shown two nuclei along with the electron cloud. If you are able to see this redness in this cloud, then here you see the redness is more on the left side, and on the right side the redness is less. So more the electrons, more the redness, more the electrons, more the electrons, more is the induced magnetic field. So B prime, you can see that the B prime in this case is more as compared to B prime in this case where the electron density is less. So with the result, you see the B effective is less for this case where the electron density is more, and B effective is more for the right case where the electron density is less. So both these are cases of more shielding and less shielding. Please remember, the books describe it as shielding and de-shielding. None of these is a case of de-shielding. Both are a case of shielding, more shielding and less shielding. So you please remember, this is not at all a case of de-shielding. So what is the effect of shielding? The effect of shielding is that the nucleus experiences a less net magnetic field as compared to the applied magnetic field. And greater the externally applied magnetic, more is the shielding, more externally applied magnetic field has to be increased. We have to apply higher externally applied magnetic field to bring the nucleus to resonance. So that means the absorption would be shift to the higher field. Why? Because now we have to neutralize the contribution of this B prime of the induced magnetic field. So we can say that the nucleus is shielded from the full force of the external magnetic field. So B effective for a shielded nuclei for shielding would be B0 minus B prime. And a shielded proton requires stronger magnetic field to produce an absorption signal, and it absorbs upfield. So in short, we can say greater the electron density around the proton, greater will be the shielding. And the reverse of this effect is de-shielding. That is, if the induced magnetic field somehow reinforces the applied magnetic field, somehow, because this is not a case of de-shielding, although many books describe it as a case of shielding and de-shielding. If the induced magnetic field somehow reinforces the applied magnetic field, then it is a case of de-shielding. That means for de-shielding, B effective is equal to B0 plus B prime. And a de-shielded proton requires a weaker magnetic field to produce an absorption signal, and it absorbs downfield. And nu is equal to, that means nu is equal to gamma B0 by 2 pi. Now it has been modified to nu is equal to gamma B effective by 2 pi. And B effective for shielding is B0 minus B prime, and B effective for de-shielding is B0 plus B prime. Or we can say nu, the Larmor frequency, is directly proportional to B effective, not directly proportional to B0. So we can say now the B0, that is the applied magnetic field, is the same for all the protons, but effective magnetic field may not be same. So now we reach a stage where my molecule is having many different kinds of protons, different types of protons. So the externally applied magnetic field is same, but the magnetic field felt by those different types of protons is not the same. So that justifies, that tells us in the story that why we get signals at different positions for different protons, or we can say the number of NMR signals would be equal to the number of different types of protons. Say for example, in case of ethanol, we have 3 protons of one kind, 2 protons of another kind, and 1 proton of the other kind. So this is a cartoon showing that we get 1 signal for CH3, 1 signal for CH2, 1 signal for H, because the Larmor frequency of these CH3 protons would be different as compared to these 2 protons, as compared to this 1 proton. So we can say number of NMR signals is equal to number of different types of protons. May I know up to what time I should continue, because the format, because I can break given if I'm given a.
Yeah, I think we can continue tomorrow from this.
Okay, so I'll just I'll just break after this one slide after discussing this equivalent and non.
Yes.
Okay. So now we say that the number of NMR signals is equal to number of different types of protons. So that brings us in the story to the concept of equivalent and non-equivalent protons. So what are equivalent protons? What do we mean by different types of protons? What do we mean by equivalent or non-equivalent protons? Equivalent protons means sets of protons having identical environment. That is one signal. They will give us only one signal. And non-equivalent protons means protons with different environments. So in different environments, they will give us different signals. And how to find out if the protons are equivalent or non-equivalent? We can find it out by a simple test, proton replacement test. Although we can find it out by symmetry also, by topicity also, but that's a little advanced as compared to this. So I'll say that we can find it by a proton replacement test. What is a proton replacement test? In a proton replacement test, whatever protons you want to test, whatever hydrogens you want to test that whether they are equivalent or not, what you do, you replace one hydrogen at a time with an arbitrary group, real group or atom. and then try to see that whether you are getting the same identical structure or an enantiomeric structure. If you are getting, by after the replacement of the hydrogens, two different hydrogens in a molecule by a test group can be real, it can be imaginary. If you are getting the same or enantiomeric structure, then the hydrogens are chemically equivalent. For example, in chloroethane, these three protons, you see these hydrogens of the methyl, once you replace this H, let us say this Z is Br, bromo. So you replace one H with bromine. Here you replace this hydrogen with bromine and this with bromine. What you get, in every case, you get one bromo, two chloroethane. So you are getting identical structure, the same structure. So we'll say they are equivalent protons and we classify them as homotopic. On the other hand, if we get enantiomers, for example, in the chloroethane, this CH2, when I replace this one H with bromo, this with bromo, in both cases I get one bromo, one chloroethane, but I get enantiomers. So again, these two protons are equivalent, but they are not homotopic, they are enantiotopic. On the other hand, if the structures obtained by replacement of two different hydrogens in a molecule by a test group are diastereomers, then the hydrogens are non-equivalent. Say, for example, in this case, one is trans, one is cis. So both these hydrogens, they would be non-equivalent because now we are getting diastereomers. So these are non-equivalent. So we'll get three peaks here, 1, 1, 1. So we'll get three peaks here. And so for example, here you see chloroethane, these three protons are equivalent, these two protons are equivalent, but these three hydrogens are not equivalent to these two. So we'll have non-equivalent protons. So three protons equivalent, two protons equivalent, but these three protons are not equivalent to these two protons. And with the result, we get two peaks in NMR. So, and we get the two peaks here. So I'll stop here and we'll build it up from this stage tomorrow. Yes, over to the host, please.
Wonderful, just Professor Pawan, this is wonderful lecture. And there are a lot of questions in the chat box also.
Okay.
So there are many comments and many questions. And dear participants, you have noticed, you must have noticed, and that Professor Sharma is a wonderful and expression. You can see how well he has explained the fundamental principle. I think you will remember it for life. You will remember it for life. It was just
I only tell stories. I only tell stories. I don't teach, I tell stories because I believe that the stories are the most, they can remember most easily. And one thing I would like to say, when I share my slides, I don't see my chat box. So I am able to see it just now. And I would say that if the participants ask, that would be easier rather than you see, if I go, you see, for example, here it is the repeat the last slide. I don't know which slide we are talking about. I couldn't see.
Yeah.
Why
I noticed it, but yeah, I noticed it, but it was not good to stop you and say, please. Actually, I think the students were so involved that they were taking it as a classroom teaching. And they were requesting that please repeat.
But Professor Vanna, you see, some questions are excellent. I'm telling you that this one question, I was wondering if someone would ask me, and this is the first time someone asked me this question. This is by Namika Mehta. It says the helium has negative gyromagnetic ratio, and what this depicts. You see, this is a question which I was always wondering that no one asked this question, right? But this is curiosity. That tells me that the participant, especially you see this participant, was listening to this and is very curious to know, very carefully. So you see, I think that I can explain it. It doesn't matter, but this is a wonderful question. For the first time, somebody asked this. So basically, you see, it is most of the nuclei, they have positive magnetogyric ratio, but few nuclei and electrons, they have negative values. Now, when the gamma is greater than 0, that means positive, then then the spin and magnetic moment, they point in the same direction. They are pointing in the same direction. Spin is also pointing in the same direction, and the magnetic moment is also pointing in the same direction. That is positive. For negative magnetic ratio, they are still collinear. They are collinear. They are not diverging. They are collinear. But the spin and the magnetic moment are in the opposite directions. That is the reason that they have the negative this magnetovaric ratio. But for studying NMR, it doesn't make, for studying it as a tool, it doesn't make a difference to us. So very nice, this Namika Mehta. Very good. This is the question which someone asked me for the first time up to now. Why spin get reversed when we apply radio frequency waves to it? You see, that is the fundamental. That's what I'm saying. It gets reversed because if you study UV, if you study any spectroscopy, whenever we have two energy levels, E1 and E2, there has to be a transition between E1 and E2. And what would be the transition here? What is the E1 and E2? At E1, the spin is, if the spin is to the top, then at E2, the spin is to the bottom. So it cannot do anything else. When we apply energy, it has to jump from E1 to E2. And jumping from E1 to E2 in case of NMR is only the spin is reversed. That is what I explained. So if you would just go back, I think that you would be able to figure it out. So I think that if questions can be asked, that will be wonderful. And if time permits to you, I'll be very happy.
There is no problem. And I think some questions, they are very fundamental and you answered them during the lecture. And dear students, we will be putting this lecture on YouTube. And I advise you to please go through the recording also. Tonight, you can go for the recording. And I think many answers will be delivered if you will be repeating the lecture, if you will be watching the recordings. And I think Professor Sharma must be tired because he delivered the lecture very emphatically and he needed a break. And dear students, as Professor Sharma is saying that you are invited to ask the questions yourself, okay? And tomorrow I will ensure that recording is on the YouTube. So please go through the recording and many questions will be answered. And tomorrow, in the tomorrow session, you can ask for your queries, which will be pending, and you can ask directly. Okay? And I think we can break here for today.
Sure, we can break here, no problems. I'll continue tomorrow. And,
yeah.
So
you want to say anyone who want to say anything or any question you want to ask personally?
Ma'am?
Yes.
Sir, I had a question. Like many times we see we use UV visible together in spectroscopy. So can we use other bands together? Like why we use only UV and visible together? Why not IR visible together?
Yeah, you see, first thing is that the fundamental, this is a fundamental question and I'm happy you're asking fundamental questions. You see, what is spectroscopy? All spectroscopy, if I'm standing in front of you on a board with a chalk in my hand, I can simply draw two lines, one at the top and one at the bottom, and I can write E1 and E2 and I can explain any spectroscopy on that. Now your question, why we use UV visible together? We do not use UV visible together. We happen to use it together because we come across, we are using the energy within that range. There are many times when we do not go into the visible, we only use UV. And many times when we use spectrophotometric methods, we are using only visible. So Priyal, it is only a question of that how much energy is required for the transition that I am interested in. Or more fundamentally, we do not study anything in spectroscopy. I gave one sentence that it is our smartness, what we can extract out of that spectrum. What is that spectrum? We are only measuring the energy difference between different states. The states can be electronic, the states can be vibrational, states can be rotational, or states can be nuclear spins. All spectroscopies, we only measure the energy difference between E1 and E2. And then we apply that information of that energy gap, that band, to reveal it, to use it for the structure determination. So we can use any together depending upon that UV visible because they are doing the similar kind of excitations. But bond rotation and you see the microwave, those two kinds of, if we do together, we'll get two different spectrums, two different kind of excitations. So it is only about the energy difference and we can use it. Hope that my answer makes some sense to you, Priya.
So that means, can we use somewhere visible and IR together?
Yeah, if we can have those excitations together, we can use it. And tomorrow we can have the hyphenated technique of IR and UV. If we can interpret both those excitations simultaneously. Because remember, the photon, the energy has to be quantized. And
Yes.
IR and UV, one is electronic transition, another one is vibrational rotational. So they both would give me a different kind of spectrum. Whereas in case of UV visible, it is the same, everything is same, only different atoms, different nuclei, different molecules would absorb different energy within that range. I hope you are getting me. Microwave and IR or IR and UV together would not give me one spectrum. It would give me two because the excitations would be two. The energy levels E1 and E2 would be different. Vibrational rotational versus the electronic, right?
Okay. Thank you, sir.
So I think we can have other queries tomorrow. Okay.
Sure.
So we are thankful to Professor Sharma for accepting the invitation and delivering the lecture. And students are really very happy. And you can understand it from their queries and from their questions and from the comments in the chat box. I can feel it. So I am highly thankful to Professor Sharma for accepting the invitation. So see you tomorrow. Till then.
Yeah. Thank you, Professor Vanna. I'm thankful to you for taking me out of that guilt, feeling of
All
guilt.
the pleasure is mine. And I will tell the other stories tomorrow. I will tell the other stories to the students about Professor Sharma Antarctica visit and how he was coming for the student conference and it dropped last minute dropped. But we are very happy and we are very thankful that he agreed to, because NMR is the technique which we should know, and all the even research students are also there. In your lecture, it is being attended by research scholars also. Okay, so thanks a lot. So see you tomorrow.
Thank you. Yeah, thank you.
Then
Thank you very much. So tomorrow again, Professor Vanna, from 4 o'clock to, I would be speaking up to what time? Because then I'll tune it accordingly.
Yeah, I think, see your session, I think tomorrow there will be many queries and it will be, I think, 1 hour and 30 minutes or more. So accordingly, okay, I think.
I'm saying you just tell me for how long I can speak because I'll tune it accordingly. Because you know NMR is very hard.
Because today even, I tell you, I myself was engrossed in the lecture and it was you who pointed out the time. Then I checked the time that it is 5:11. Okay. So I think you should restrict your talk up to 4:45 and then we can go for the queries.
Okay, 45
Otherwise,
minutes.
4 to 5, because students will have many queries.
Students, I don't mind as long as it's not causing any disturbance at your end. I think then 4 to 5. Give me 1 hour because that I would need.
No problem. Our end is no problem because the Zoom platform is paid and it is unlimited. Time is unlimited. So we don't have it. But
I don't mind if the queries would be up to 7. Doesn't matter, right?
Okay.
So with me,
okay. So nice of you. Thanks a lot.
Yeah. Okay. Thank you.
Thank you.
Thank you very much.
See you tomorrow.
And please share the YouTube link with me also.
Yeah, sure. Okay, then bye.
Yeah, okay. Have a nice day.
Yeah, same. Bye, participants. See you tomorrow. Okay, so now I will leave. Goodbye.